Hi everyone, I'm Sam Liu from the University of Texas at Austin, and I'm happy to present our work with Sandia National Laboratories on hardware-aware Bayesian variational inference using magnetic tunnel junction noise distributions and artificial synapse arrays. So first of all, what are Bayesian neural networks? So we like neural networks because they can help us do classification and regression and a lot of other cool things. So the difference in Bayesian neural networks between that type of network is that the weights are encoded as distributions instead of deterministic values. So your output would also be a distribution. BNNs are typically trained using variational inference and backpropagation, which means that these arbitrary distributions for these weights are decomposed into just two parameters, mean and a standard deviation, and all the weights are regarded as Gaussians. So why are BNNs useful? Well, they can perform uncertainty quantification. So that means they can tell you if your data is noisy or if it's perfect, or if even if the data coming in is out of distribution. So this provides an opportunity edge computing because let's say you have a robot that's just floating around in space, that's getting some images and you want it to be making decisions on its own based on those images. Well, um, another important aspect to consider is how well your training was done and if it's the data coming in is unreliable or out of distribution. So we propose a device, Bayes-MTJ, that can encode these stochastic distributions. So Bayes-MTJ utilizes a circular in-plane MTJ that relies on thermal fluctuations to encode the noise. So the thermal fluctuations cause the magnetization to spin freely in the free layer, and so therefore the noise range is the full range of TMR. And you can change TMR using VCMA, voltage controlled magnetic anisotropy. Obviously, you don't want to apply voltage for every device within an array. So there's room for some material innovations in either magnetoionics or ferroelectrics in order to make sure that we can engineer some non-volatile noise states into the device. In any case, we simulate this using a thermal Landau-Lipschitz-Gilbert macrospin model. As you can see from the plot, conductance noise is being generated over time, and as you change the effective built-in voltage, then the range of the conductance noise also changes. So here we show how to integrate Bayes-MTJ into a crossbar array. So here we have one Bayes-MTJ device for noise and two devices to encode the weight. The weight encoding devices we choose to be domain wall magnetic tunnel junction devices, and all you need to know is that here we account for 16 level notch quantization and also average noise output from the device in the cross and crossbar simulator we use later. So in the special bit cell, we have a special read scheme used to output noise from the device. So as you can see for the top device, the first part of the read pulse is positive, second part of the read pulse is negative. Well, when you integrate the currents on the output, it becomes a zero-centered conductance noise that you can change by changing the voltage. So to what extent can we control this noise? So from the plot on the very left, we can see that actually the faster you sample it, the more you get some maximum conductance noise out of it, which is nice. So which means that the faster you try to make it, actually the better your noise range should be. For an effective built-in voltage calculated between 0 and 5 volts, you can achieve a 38.9 to 1 noise standard deviation ratio, or on-off ratio, which is will show to be quite effective. And then the next plot is of the distribution that's output from the conductance noise element. It's non-Gaussian, but it's zero-centered with a constant shape, so as a result, we can fit it analytically and use that analytical model to integrate with the crossbar simulator. So here we have a convolutional Bayesian neural network with the LeNet5 architecture. So this is already pre-trained on fashion MNIST. And as we can see, the standard deviation ranges fall very nicely within the range that our devices can represent, except for COM0. But basically, COM0 is really close to zero standard deviation, so you can just turn off the device and use the deterministic weights like that. So here are kind of the results of the training. So the networks are trained and evaluated on Fashion MNIST in figure A, and they're also evaluated on EMNIST letters as the out of distribution data set in figure B. So you can see figure B, all of the networks kind of have a higher total uncertainty than in the case for A because it's out of distribution. When we look at the figure C, this is a calibration curve. And so what we want to see out of it is that we want the confidence in percentage to be approximately the same as the accuracy in which it's classifying these images. So that's represented by the dashed black line, and the software BNN and spectronic BNN both are well calibrated to fall around this line, but the software DNN consistently is overconfident. And then we can also extract a scalar value out of this plot. The expected calibration error, or EC, it basically describes a deviation away from the calibration curve. It's the sum of all of these test cases. In order to get a clear picture of what's going on, we construct a data set that's a gradual transformation from Fashion MNIST to EMNIST letters, from 0% to 100% letters. And as we can see, throughout this entire transformation, both BNNs maintain lower ECs through the entire transformation, and the spintronic BNN performs similarly to the software BNN. So to speak on the co-design aspect, how much noise contrast is needed for the Bayesian MTJ? And it turns out not that much. So for this specific task, the ECs are reduced to under 10%, even for an on-off ratio of approximately 7:1, which is much better than we originally assumed. So the next question is, how can this do at higher complexities? So here we have a resonant architecture. We apply it on a CFAR 100 image classification task. So first we extract the weight values, and immediately we kind of see that in levels 10 and 11, there's a big spike and maximum noise standard deviation. And that's because that means that our devices are not able to fully encapsulate the maximum noise range of the layers. And so as a result, we expect that it should slightly suffer compared to software. And while it does suffer, it still does quite well for higher complexity tasks. So our out of distribution data set used is Street View house numbers. But as you can see, so in that plot, the software BNNs in blue are really well calibrated to the black dashed line. Spintronic BNNs are slightly overconfident compared to the software BNNs because they're just slightly less noise that it's not able to represent, but still much better than software DNNs, which have ECs that are much higher than those of both BNNs. And the base MTJ is also excellent for regression. So this is kind of a killer application of BNNs because BNNs are unable to provide uncertainty for regression. And as you can see here, the spintronic BNN pretty much matches the performance of the software BNN. So the final part of the story is that the Bayes MTJ is fast and also energy efficient. And so neural network accelerators, multiply communal operations, or MACs, dominate the energy usage. And as you can see from the first figure, even at moderate array dimensions, MAC normalized energy is greatly reduced due to the crossbar, and it's around 100 times improvement over CMOS for larger arrays. And for plots B and C, you kind of have to evaluate how many samples do we need in order to produce a well-calibrated inference. And for a small task, even one sample is pretty much enough for high accuracy and low ECE. But for harder tasks, CFAR 100, more samples are needed. So it kind of depends on your task. So in summary, our proposed Bayes MTJ device architecture in BitCell seems to perform quite well. So near ideal inference accuracy for smaller networks and tasks, and high inference accuracy for deep BNNs. And energy efficiency wise, we show that they can be up to 100 times more energy efficient than CMOS TRNG for larger networks. And all this indicates that they could be good candidates for BNN accelerators. Thank you all.